Humanity is right on the edge of its most ambitious mission yet, a relentless high-stakes race to establish a permanent presence on the moon by 2030. But to truly wrap our heads around the sheer magnitude and honestly the deadly stakes of this next step, we have to start with a dramatic journey. So picture this. You're 230,000 miles away from Earth. Utter silence. The desolate, freezing surface of the lunar South Pole is waiting directly below you. Imagine hanging out there in the absolute void of a total vacuum. You're falling toward that jagged, gray lunar dust, and you are entirely dependent on one engine, just one. And here's the terrifying reality of deep space. If that single piece of machinery fails, if a microscopic valve sticks, or a tiny seal ruptures in the cold, there's no backup plan. There's no rescue mission coming. You simply become a permanent, frozen part of the lunar landscape. Now, that chilly scenario, it's not science fiction. It is the exact mathematical problem keeping aerospace engineers wide awake at night right now. It sets the stage for what is essentially a high-stakes duel. Because as we race back to the moon, we're looking at two completely opposed blueprints for human survival. Do you trust the proven, battle-tested legacy of absolute simplicity? Or do you build a massive, highly complex fortress of redundancy? In this explainer, we're going to impartially unpack this incredible fundamental engineering divide between the United States and China. Just look at this headline for a moment from South China Morning Post. This is the news behind today's video. Chinese team flags life-threatening, glaring weakness in NASA's Artemis program. Researchers say China's lunar lander has 3 backup engines, unlike US design, which relies on one main power source. With that said, let's go straight to the intro. The algorithm buries channels that show the truth like mine every single day. The only thing that fights back is you. 1 like, 1 subscribe, turn on the bell icon. That's how the truth about China survives on YouTube. Don't let it disappear. Thank you very much. Section 1. The engine failure dilemma. Single point of failure versus safety nets. Okay, to really understand this modern space race, we have to look at this core architectural divide. For decades, the American philosophy has rested on a very specific approach, dating all the way back to the Apollo era. It's the tradition of component simplicity. And honestly, the historical logic is super sound. Every single time you add an engine to a spacecraft, you're adding hundreds of failure-prone valves, complex plumbing lines, and some incredibly intricate software. By relying on one single, highly tested, incredibly reliable main engine, you literally eliminate those extra failure points. But then we have China's emerging strategy of systemic redundancy. Their aerospace engineers argue that in the harsh, totally unpredictable radiation and extreme temperature swings of deep space, no single component is truly guaranteed to work. So their philosophy? You absolutely must utilize an integrated engine cluster to survive a catastrophic failure. When you dig into the data from international aerospace reviewers, a lot of intense scrutiny has naturally fallen on this single engine reliance. For critical life or death orbital maneuvers, NASA's Orion spacecraft actually utilizes the AJ-10190. Now, this is a highly reliable but refurbished engine from the 1980s space shuttle era. While its track record is historically excellent, critics point out a stark reality. If it fails during lunar orbit insertion, well, the mission effectively ends. And this concern is compounded by some technical hurdles flagged in NASA's very own Artemis 1 post-flight data. They noted unexpected heat shield delamination and nitrogen leaks in the main propulsion lines. It really highlights the inherent nerve-wracking risk of placing human lives on a single point of failure in an environment that is, quite frankly, actively trying to kill you. Section 2. Lanyue's engine redundancy strategy, embracing the moon with a 26,000 kilogram fortress. Let's pivot over to China's Lanyue lander, which, by the way, translates to embracing the moon, and see a completely different paradigm for human survival. Instead of one massive central engine, Lanyue packs a cluster of 4 YF-36 variable thrust engines. According to the design specs, these are powered by storable hypergolic propellants. Now, these are highly toxic chemicals that literally ignite spontaneously the very second they make contact with each other. So why use them? Because they massively increase the reliability for engine restarts in the freezing dead vacuum of space. But bolting 4 engines to a ship creates a brand new terrifying physics problem. What happens to the delicate balance of the spacecraft if one of those engines suddenly dies mid-descent? Well, if one engine fails, the thrust instantly becomes asymmetrical. The lander would immediately be thrown into a rapid, fatal, uncontrolled roll. To combat this, an incredibly rapid guidance, navigation, and control system was developed. Here is the exact sequence of how it works. Step 1. Sensors detect a pressure drop in mere milliseconds. Step 2. The computer entirely bypasses human input and instantly shuts down the engine diagonally across from the dead one. Step 3. This brilliant software intervention immediately restores perfectly symmetrical thrust. And finally, step 4, even running on just 2 remaining engines, this heavy lander possesses enough power reserves to execute an adaptive abort trajectory. It can either rocket back up to the safety of orbit or calculate a new delayed landing path. It's an absolutely stunning software solution to a deadly hardware danger. Section 3. The Shared Bulkhead Breakthrough, Solving the Mass Penalty. Now, any aerospace engineer looking at Lanyue's blueprint would immediately raise a massive red flag. Adding 4 separate engines, hundreds of meters of extra plumbing, and complex manifolds, that should incur a massive mass penalty, making the lander way too heavy to ever leave Earth's gravity. To offset this, material scientists had to invent a true structural miracle, the Shared Bulkhead Propellant Tank. Traditionally, fuel and oxidizer are kept in completely separate tanks, which means you need thick, heavy walls and massive structural support rings. But this design integrates them into one single cylinder, separated by just an ultra-thin common wall. This breakthrough totally eliminates the extra exterior shells, saving hundreds of kilograms of dry mass and allowing them to install that heavy, redundant engine cluster without blowing up the launch weight. But this weight-saving miracle comes with a really terrifying trade-off. To keep that ultra-thin shared wall from violently imploding or rupturing and prematurely mixing those explosive chemicals, the pressure on both sides has to remain perfectly equalized. Automated valves must maintain what can only be described as God-tier pressure control. They have to limit the differential between the tanks to a razor-thin margin of just 0 to 0.3 megapascals. A fraction of an error here and the ship is lost. It is an astonishing high-wire act of precision engineering. Section 4. Artemis versus Lanyue, a clash of the lunar heavyweights. Let's dive into the mission parameters and directly compare Lanyue with the massive commercial designs NASA has selected for the Artemis program. The data reveals how Western commercial partners are pushing redundancy to an entirely new extreme. Just look at the specs for Starship's human landing system. While China uses 4 main engines, SpaceX utilizes 6 massive Raptor engines, plus an incredible ring of 18 secondary landing thrusters. Furthermore, Starship is fueled by complex cryogenic methalox, and while methalox offers incredible raw performance, it risks boiling off in the harsh environment of space. That's a stark contrast to the highly stable, albeit toxic, storable hypergolic fuels. But what truly separates these philosophies is the sheer jaw-dropping difference in physical scale. Lanyue is a compact, highly optimized, 5-meter-tall reusable workhorse. It's designed for specialized transport. SpaceX's Starship? That is a towering 50-meter steel behemoth. They are essentially attempting to land a 15-story skyscraper on the uncharted surface of the moon. Landing a 15-story skyscraper on unprepared, dusty lunar regolith creates a terrifying physics anomaly known as a rock tornado. If Starship fired its primary Raptor engines all the way down to the surface, the immense downward thrust would dig a massive crater, instantly destabilizing the ship. Worse, it would kick up high-velocity, jagged rock debris that would act just like shrapnel, completely shredding any solar panels, equipment, or habitats nearby. To mitigate this catastrophic threat, SpaceX engineers designed a brilliant workaround. They'll shut off the main engines high above the surface, switching entirely to that secondary ring of 18 mid-body thrusters. Positioned high up on the hull, they fire outward, gently lowering the behemoth to the ground, without triggering a deadly debris storm. Section 5. Next steps for humanity. The race to 2030 and beyond. As we look at the timeline ahead, the stakes honestly couldn't be higher. Both nations are rapidly moving from digital blueprints to burning metal at an astonishing, relentless pace. Just look at this methodical testing schedule. In merely 8 months, a massive high-altitude vacuum simulation stand was constructed in Shanxi. By August 2025, integrated exogravity tests were completed in Hebei. They actually used massive tethered towers to simulate 1/6 gravity, dropping sensor packages over rugged, cratered terrain to test autonomous avoidance. It's an aggressive mathematical push toward a crewed landing by 2030. All to lay the absolute groundwork for their ultimate goal, the permanent International Lunar Research Station. And really, that's the ultimate takeaway from all this data. Machines like Mengzhou, the Dream Vessel, and Lanyue embracing the moon, alongside America's Orion and Starship, are not just landers trying to win some geopolitical race. They are the permanent architectural foundations for humanity's next great era. They are the critical next steps for our long-term expansion out of Earth's orbit, deep into the solar system, and eventually onward to Mars. The engineering happening right now behind closed doors across the globe is nothing short of a revolution. But space is entirely unforgiving, and physics absolutely does not care about national pride. As we wrap up this explainer, we want to leave you with this final thought. If you were the one falling toward that lunar surface, which philosophy would you trust with your life? The meticulously synced complex fortress of redundancy, or the battle-tested, unforgiving legacy of absolute simplicity? We really want to know what you think, so drop your thoughts in the comments below. Hit subscribe to join us for our next deep dive into the unknown. Keep your eyes on the stars, and goodbye.